All right. Hello, everyone. Welcome to 365. We are on our second module now. So let's do a quick little recap. Hopefully, you're all aware that Talking Web's deadline has passed. I'm going to give this speech probably at the end of every module. So there's some level of instability on the site the closer and closer we get to the deadline. So my goal is to resolve this. Unfortunately, the practical reality is that it is not resolved yet. The reason for this instability is that half of the class is working on the assignment in the last few hours before the deadline. So suddenly our usage goes up like 10x. So while I'm going to try to resolve the instability, unfortunately, I think that it was only really down for like 5-10 minutes, though there was some slowness. The reality is I encourage everyone to start early. We're not going to make extensions. I mean, unless the server really goes down for like hours at a time or something crazy like that, we're not going to make extensions for this. So if you don't want to deal with site instability, pretend the deadline is the night before and you will not deal with any instability. So I know I'm saying this, and I know half of you will still continue to do this the hours before it is due. But I'm just telling you, your experience will be significantly smoother if you do it the day before. That's just how it is. Okay, I know it's unfortunate, but hopefully, maybe as soon as possible, we're trying to get more servers up so that we can handle that increased spike, but that's just the reality right now. Does anyone have any questions about that? Hopefully it's like intuitive that there's like a 10x usage at the deadline. All right, cool. So the deadline has passed for the first assignment, and we are now into the second module. So on Thursday, I previously started discussing x86-64 assembly. This assignment is due in 8 days, and then after that, the next assignment will open, and then the next assignment will open, and so on and so on. And we'll just constantly have assignments. So as we're all aware from syllabus day, 100% of your grade is assignments. We don't necessarily make that mean that this class is easy. We constantly have assignments. So 9 assignments. All right. Hopefully that is a good meta discussion of the class. Yes, we are streaming, right? Twitch TV. Well, we'll let someone say that we are streaming. Okay, cool. So we are going to resume discussing x86-64. So I previously pulled on the Thursday class, but as you hopefully are all aware that you're responsible for watching both. But I'm going to ask the same question anyways today. How many people have learned some form of assembly in a past course? Okay, so most people. So this is mostly a refresher for people. That being said, it is a different assembly probably than most of you are familiar with. Probably just about everyone that rose their hand is referring to MIPS assembly. We're discussing x86-64 assembly. Very similar in nature, but technically different. Cool, I am in fact streaming. All right, so we are going to resume discussing it then. As a recap, we have this test.s file that we were previously using on Thursday. And this demo code where we left off, let me actually reopen this file. I guess we lost it. That's okay. We effectively wrote something that looks like, so let's take this. So if we look at this, we started by initializing RAX and RBX to 0. So that in the C world is RAX equals 0, RBX equals 0. And then we have this loop label. So this is something that other parts of the program can refer to. We compared RBX with 2. And if it's greater than equal, we go to done. Otherwise, we fall through, we add 2 to RAX, we add 1 to RBX, and we jump loop. So put in another way, what this means is we can kind of convert this into a while true. So we see that there's a loop and then a jump loop. So this is kind of in a loop forever. We're just going to say forever right now. We know it's not forever. So we'll say while true what we do, we'll ignore this comparison stuff for a moment. We say RAX plus equals 2, RBX plus equals 1. And then let's go back to this. So compare RBX with 2, jump greater than or equal to, done. So these two instructions kind of flow together as like this one concept, basically. So what this means is that if RBX is greater than or equal to 2, we go to done. So done right here, we'll just say done. And we say if RBX greater than or equal to 2, break, right? So this is what we implemented in assembly. So just a handful of instructions is basically just as many lines as it is C, right? It's really not too much more. One thing that I will remind you of, and is a consistent issue, one of the primary benefits, in fact, of C, besides having nice control flow constructs, is the fact that you don't have to manage your registers. The compiler automatically handles your registers for you. So we can have an infinite number of local variables here. We cannot have an infinite number of registers. There's a finite number of registers. And that is how this works. So as we know, or I guess maybe not immediately clear, we can start reorganizing this code. So rather than being while true, what we can do, this program right here is the equivalent to if we say RBX is less than 2. So while RBX is less than 2, because the very first thing we do if it's greater than or equal to 2 is break. So while it's less than 2, we do this. So this is kind of a simplification. Both those programs are equivalent, but this is, a nicer, less confusing version of that program. So something I didn't show last week, and I'm going to save this file. We'll say test.c, is if we compile this, so what we're going to do is we're going to say GCC. So GCC is just another, oh, there's a question? Yeah.
Could you just real quick re-explain like RAX, RBX, like what are those?
Yeah, so RAX and RBX are registers. So these are 64-bit values. I guess before we go through this GCC step, let's run this. So if you missed last week's, highly encourage you to watch last week's because we're continuing on from that. But what we have here is a bunch of registers, and each of these registers can hold 64-bit values. So what we do when we do move RAX 0, I mean, RAX is already set to 0, but when we execute that instruction, guess what? RAX becomes 0, nothing really changed, but for clarity's sake, we are initializing these values to 0 explicitly. We set RBX to 0, and then we hit this loop part of the program. So we compare RBX with 2. So RBX is currently 0. So this comparison is going to say something to the effect of these are not equal. It's going to set the flags registers. We don't really need to look too much into the flags registers right now, but that's how that mechanism works. This is setting flags registers. And when we compare it, the flag registers basically says that, hey, these things are not equal to each other. So when we do this check of jump greater than or equal to, this is not true. In fact, it's less than. RBX is less than 2, so we don't follow this jump. So then we go to this add 2 to RAX. So we step through that. Suddenly RAX is 2 larger. We step forward. Suddenly RBX is 1 larger. And then we go back to the loop. And now we're checking again. Hey, is RBX equal to 2, less than 2, greater than 2? What the heck is RBX's relationship with 2? It is still less than 2, so we are not going to follow this jump. We are going to again add 2 to RAX, so now RAX is 4. We are going to again add 1 to RBX, so now RBX is 2. And we are going to do it all again. So now we're going to again compare RBX's relationship with 2. Is it less than? Is it greater than? Is it equal to? What the heck is it? At this point, we are suddenly greater than or equal to 2. So we are now going to follow this. You're going to see that we don't continue executing this. The way that we're displaying this to you, it's going to suddenly jump to the done label. So if I hit step, we are at the done label and we've broken out of this loop construct. So that's kind of what's happening if we execute through this instruction by instruction. So what I wanted to demonstrate for you is that who here has used GCC, right? Everyone has used GCC, right? This is not like, okay, good. Hopefully everyone's used GCC before. This is how you compile a C program. So if we GCC test.c, and we're going to produce, we'll just call it test C underscore C or something. We now have this test underscore C program. So all GCC does, and I say all kind of jokingly, it's kind of a big task, but it's just a program that goes through, it parses this, and it more or less just spits out x86 assembly. That's all GCC does. It's just another program like any other program. It just translates this into something that looks kind of like this. The way that we can prove to you that it looks kind of like this, is not identical, but hopefully it'll be very similar, is, and there's going to be some instructions that we haven't seen before, but we're just for sake of explaining it or showing it. If we obj dump this thing, so obj dump is a program that lets us take, well actually before I do that, let's obj dump our initial test program. So I am passing -D to disassemble this thing, -M Intel to use Intel syntax, and I'm going to do our original test.s program. So if we look at this, we're going to see it says, hey, this thing is an ELF64 x86-64. In the world of Linux, an ELF is kind of like a .exe in the world of Windows. It's kind of, that's the file format for storing all of these instructions as well as other data, and then being able to load that and start up a process. We've got our start symbol, we've got our loop, we've got our done. And you can even see the bytes here that are responsible for these instructions. So we can see this comparison instruction is 4 bytes long. This jump greater than or equal to is 2 bytes long. And each instruction has a different size. So this is a big difference from MIPS. Every instruction in x86, there's a whole bunch of different sizes. It's not just 4 bytes or whatever the heck MIPS is. I think it's 4 bytes. We have different variable length instructions. So if I do the same thing now for our C version of this program, it's a bit more complicated of an ELF64, but if I jump all the way down to the main symbol right here, so as I said, there's more instructions involved, but we previously looked at setting up memory. So as I said before, C, actually, you know what, before we go down this path, I'm gonna compile this program with optimizations. I think it'll actually make the code clearer. Let's do 03. Let's see if that in fact does make it clearer. I guess it's not able to do that. Whatever, we'll roll with it anyways. So what we see here is that we load up the value 0, and instead of loading it into the RAX register, we load it into memory. So we're loading it into RBP, which is some other register. We'll ignore what the heck that register is, but it points somewhere in memory. And RBP minus hex 8, this is a location in memory. So similar to how in our test.s, similar to how in our test.s we load into RAX 0, this is loading in 0 somewhere into memory. And then we load 0 somewhere else into memory. And then we immediately jump to main plus hex 20, which is address 1149. So right here, 1149. And we do this comparison. So it implemented it a little bit differently. Instead of comparing with 2, it's comparing with 1. But there you'll see that instead of greater than or equal to, it's doing less than or equal to. It's equivalent logically. It compares this value with 1, jumps less than or equal to, if it is less than or equal to 1, it jumps to 1141. It jumps to here. So in that first pass, we are less than or equal to 1. So we do our add stuff, and then we compare again. And then we do our add stuff, and then we compare again. And then eventually we are not less than or equal to, and so we break out. And we go here, we move, this is basically the finish up. So this program is slightly different, but hopefully you can see that it is equivalent. These two sets of assembly are equivalent. It's just that GCC decided probably this is a little more efficient than what we did, right? See, we have like, how many, we've got like extra jumps in here. it said, we don't need extra jumps. We can do this more efficiently. It wrote better assembly than me, but these programs are equivalent. So GCC, it just does that translation. It produces x86-64 assembly. So that is how it works. And then once you have this ELF file, it's the same. It doesn't matter if it came from the C world or not. It's just the same idea. We're just loading it up and executing instructions. Okay, so one thing that's missing, that's pretty big and missing, is how do we store data? So let's say we have something like hello world, and this is just a piece of text. How does that interact with this? So let's pretend, for example, that we want to run an algorithm. We want to compute the length of the string hello world, and then maybe we want to compute the length of another string. This is a test, and then we want to compute the length of another string, and so on and so on. How do we make a real program like that? So what we're going to do is we're going to show off another thing that exists within assembly, and that is called dot section. So there's different sections of memory. So if we look at the obj dump of our initial program, you'll see it says disassembly of section dot text. It's probably unintuitive, but the dot text section is like the code section. This is where all of the code lives. This is the text section. We can also have a data section. We currently didn't define one, but we're going to go ahead and do that now. So if we do dot section data, and then we do dot string hello world, and we make this program, and then we obj dump this program, we're going to see that we now also have a new section. We have the data section. And the way that we have obj dump running, it's trying to treat all of these bytes as if they're x86-64 instructions. So this, I don't expect you to understand what the heck these instructions are. It's just wrong. Obj dump is deciding to treat these as instructions because you could treat these bytes as instructions, but for our purposes, these are not instructions. Right here is hex 48. Does anyone know ASCII or have seen ASCII before? Is ASCII a word you've heard of? Yes, a lot of people have heard of ASCII. Does anyone know what hex 48 is in ASCII? Yes. It's an H, exactly. It's not surprising. It is this H byte right here. And here's how we can prove that. If we create a new terminal, we're going to do this so that it's smaller. And we do man ASCII, we are going to see this ASCII table. So we can see it shows it for octal, for decimal, for hex, and we were looking at 48 in hex. So 48 in hex right here is the character H. The next byte is 65, hex 65 down here, 65. This is an E, and hopefully it's not surprising where we're going with this. We'll do one more, 6C. 6C is a L, right? We have these bytes for hello, comma, space, world, exclamation point, loaded up into the binary. And because of the way that we're looking at this, we're using a tool called obj dump. Obj dump is disassembling this as if it's assembly. These bytes technically also correspond with x86-64 instructions. You can treat this as if it's ASCII. You could treat this as if it's a 64-bit integer. You could treat this as if it's anything, really. You could pretend that this is beginning to decode for a bitmap image or something. If we look at this, instead of with obj dump, if we use the program xxd, what this is going to do is it's going to do a hex dump of our file that we're passing it. So if we do this, this is the raw bytes of this ELF file that we're executing. So you'll see that right at the start, so the way that this appears is this is kind of like the address or the offset from the start. So at the 0th offset, we have these bytes represented in hexadecimal. These are the ASCII characters, if there is a corresponding ASCII character. So this represents right here 16 bytes of data, then another 16 bytes of data, and so on. So we can look at the entire file. You'll see there's a whole bunch of null bytes in here. I guess the way the assembler does it, or either the assembler or the linker decides to throw a whole bunch of null bytes into this. It's probably padding it to be a page. So a page is 4096 bytes of memory. Okay, and then we have more stuff here. And you'll see somewhere in here, just raw bytes living in this file is the string hello, comma, space, world. We also have these other bytes, so 48, C7, C000. I don't expect you to have been paying attention. It's not that important, but these are actually our instructions. So we go back here and we look at, let's just do this right here. Actually, no, let's go and do obj dump. Obj dump. So 48C7 C0 000000. So 48C7 C0. Guess what? 48C7 C0. So these are our instructions right here. It's just a file. Like it's a file in exactly the same way that echo hello world into file.txt. And if I run xxd file.txt, in the same way that this is a file, and ELF is just a file. It just has a whole bunch of bytes. It's just the kernel knows what to do with this when it's loading up memory to get this program running. And then the CPU knows how to interpret those bytes, and then the rest just, it all works. It's layers and layers of abstraction. Okay, so this is our ELF file. Of course, you don't normally look at an ELF file by just looking at the raw bytes, but you can look at it like it's just a bunch of bytes. And it has a well-defined format, and it gets parsed, and things run. Okay, so back to what we were trying to do. So we now have this section data with the string hello world. So if I want to reference this string hello world, the way that I do that is I put a label on it. So similar to how I do jump loop, and now I can refer to this loop thing. What I can do is I can say hello, and this is, and we can even do this on one line if we want to. This is now something I can refer to in my code. So let's go ahead and move this from one section of memory to another section of memory. So let's go ahead, and in this case, what we're going to do is we're going to move it. Well, let's see here. Let's use our fun thing right here, and we're currently displaying this piece of memory right here. I'm going to just copy this address, and I'm going to move hello world to this location. So what I'm going to do is I'm going to say move RAX this value. So this is a location in memory, and it's a location in memory that our tool, our GDB tool that's automatically displaying stuff for us very nicely is showing. So that's why we're picking that address. And then let's go ahead and do let's go ahead and move into RAX hello. I think this is the right syntax. Let's see that this is the right syntax. If we do this, nope, too many references here. Let's see here. What we want to do, I think, is move into RBX hello, and then we will move in from RBX into RAX. We're moving into this address, or we could just take this address now that we're doing that. I'm pretty sure this should work. Nope. Let's go back to what we were doing with RAX. Okay, we got something to compile here, or to assemble for us here. So we're moving this value into RAX, so that shows up into RAX. We're taking this thing and putting it into RBX. Something's telling me that this program is not correct, because what happened is we just moved that into there. Oh, I think what we need to do is offset hello. Let's see. No. Okay. So what's currently in memory is what we're going to take a look at. I think, so we have all of our instructions over here. We look at 40200. No, it doesn't like that. Oh, wait, 40. Let's see here. Something is telling me that this is not ending up in here. Okay, what we're going to do is we're going to run another program, the strings program, on test. We do see the string hello world is somewhere in there. I'm going to make, actually, no. Oh, wait, if we do that obj dump, where did obj dump say it is? Well, it says it's over here. Make test, rmtest.o, make test. What the heck is happening? See, it's not giving us a location. Very sad to see. All right, here's what we're going to do. We're going to ignore this section stuff for the moment so that hopefully we can move along. There's no reason that this string thing can't also just live right next to our code. This is very unconventional, but there's nothing stopping us from having this label with this string. It's just a bunch of bytes. We're saying, hey, put a bunch of bytes, and when we load this program into memory, those bytes are going to appear there in memory. So we're going to ignore this whole data section thing for the moment so that we can continue making progress. And now if we look at this, we're going to see that hello has this address. We have an address assigned to it. It's going to get loaded into memory. Now we can definitely refer to this thing. Not quite sure what's going on with that data section. And we're going to roll with this. So now we can see we load up some address into RAX. So that goes into RAX. We load this thing into RBX. So that looks good. And then we take RBX and we put that into memory at RAX. So we step and we will see right here in memory now. Well, actually, that's not what we want. So we see that we did it wrong again, but we're making some progress and we're able to debug and see what the heck's going on. So that's very useful. We see that what ended up in memory is not hello world. It is the address of hello world. So we don't want to do that. I think, in fact, now what we don't want is the offset to hello. We want hello getting moved into RBX. Let's see here. So now if we step, we put that there. And now, okay, now this is looking much more promising. Now we've moved some data into RBX. So this is actually currently sitting, hello world, and not all of hello world, we'll see how much of hello world here in a second, is currently sitting in RBX. And remember, this is a little endian integer. So this means things are sometimes backwards from what you might think is intuitive, but it is all correct. The first byte is the least significant byte, which means it's right here. So that 48 that was a capital H, that's right here. This 65 is our E. This is an L. This is another L. This is an O, and so on. 2C or 20 right here. That's space. I guess that means this is a comma, and so on. You're going to see that this is not the entire string hello world, but let's go ahead and let that process. What we moved here was 8 bytes. So under this setup, as we said, since we're using registers and everything more or less, there's some exceptions to this, but more or less things are bound to 64 bits. We can only transfer 8 bytes of memory at a time. That's it. We're constrained to moving 8 bytes of memory at a time. We can move the next section as well, but so far this is all we have moved into memory. And so this is, if we look at this address right here, what we managed to transfer is hello, comma, space W. That's just 8 bytes of information that we moved into memory right here. So if we wanted to move more into memory, what we could do, and this isn't necessarily the most efficient way to do it, but it would work, is we could do add RAX8, move RBX hello plus 8. I think that syntax will work. We'll see here in a second. And then move RAX RBX, right? And now we can transfer the next 8 bytes of information. So let's run that. Let's see what the heck happens. So we got some data transferred there. and we got some more data transferred there. So we did it in 2 passes through this. And we saw what the heck it looks like to use stuff like loops. This is where loops come in. If we want to implement mem_move, right, if you've used the C function mem_move to copy a whole sequence of bytes, we could implement that. We're going to use a looping fashion because we can only transfer at most 8 bytes at a time. Maybe to make it simpler, we'll transfer 1 byte at a time. So this works, but of course, as we all know, but there is even more now. If we suddenly had this piece of text, this is not going to work. So we'll step, and now we've transferred this, which is great, but as we would expect, we haven't transferred everything. If we want to be able to transfer everything for some dynamic value, some random piece of text, what we're going to do is we're going to use loops. So we will start by using or moving into RAX this value right here. Then let's move into RBX hello. We'll do the beginning of that as well. And then what we're going to do is we're just going to, let's see here. How do we want to do this? We have a few options. Let's do this. Let's do the simplest option first. What we're going to do is create a label, and we're going to call it memCopy loop. And we're going to keep jumping to this memCopy loop. The very first thing, or the very last thing we will do, we're going to put a whole bunch of instructions inside of here. The very last thing we're going to do is we're going to jump to memCopy loop so that we can just keep doing something. So when do we exit? Well, we're going to exit if RBX is ever 0. So if RBX is 0, that means it's just a bunch of null bytes. And for now, we're going to say that 8 null bytes constitutes the end of a string. We're kind of, maybe it's not clear what's happening. We'll make it clear in a few moments. But since we're going to be transferring 8 bytes at a time, we have to, the way that we're doing this, treat it as if there's 8 bytes of zeros, that is the end of our string. We'll see that as we step through. It'll be a lot clearer. So what we want to do near the end also is we want to increment RBX by 8. So we're going to do add RBX 8. So I'm kind of writing this program in 2 directions. I'm like thinking about what do I want to do at the end? What do I want to do as part of the core of it? Well, right now, hello, actually, hold on here. Not true. We want offset to hello. So right now, RBX contains the location of what we're transferring. So hello, the location for it is currently in RBX. And then what we want to do is, let's say, move into RCX, RBX. And again, I'm not writing this very efficiently. We're just kind of like doing whatever feels the most natural at the beginning. So we're dereferencing this location. So we're taking whatever the heck is in RBX, we're pulling it out of memory, and we're throwing it into RCX. And then what we're going to do is move into RAX, the location at RAX, whatever the heck is in RCX, right? So this is move it from memory into a register, move it from register back into memory, just a different location. So this is the equivalent of this. Now, unfortunately, this instruction doesn't exist. So that's why we're writing it this way. And then we add RBX8. Well, we're also going to want to add RAX8. So the location that we're transferring to is in the RAX register. The location that we're transferring from is in the RBX register. This is what does the memory transfer. And then I guess I'm missing one thing right here. It's very easy to like forget an instruction, but we need to be able to exit this loop. We never have the ability to exit. We'll say done is over here. If RBX is 0, and I'm already noticing that this is not correct. So this right here would be if the location, right? RBX is currently a location. It's an address. It's a pointer. If the pointer was 0, well, we could get ready to exit. But that's not what we're trying to do. We're trying to do if the contents is 0. So what we'll do is compare RCX with 0, because this is the contents. And if it is equal to 0, we're going to jump to done. So, okay, this is kind of written in multiple directions, thinking through what's going on all the way through. Here's what we're envisioning. We're loading up some destination address into RAX. We're loading up some source address into RBX. We take the content at that source address, throw it in RCX. If that thing is 0, get the heck out of this loop. Jump to done. Otherwise, we're going to fall through to here, and we're going to take whatever that value is that we pulled out of memory, and we're going to push that into RAX. So this is the actual memory transfer here, I guess kind of coupled with this. And then we increment our values by 8 because we're transferring 8 bytes at a time. We add 8 to RAX, so now our destination is going to be 8 further. We add 8 to RBX, so now our source is going to be 8 further, and we repeat the whole process. All right, let's see if we wrote this correctly. So this is where debugger comes in. I think I caught a bunch of mistakes, but if this is your first time, using x86-64, which for almost all of you it is, you're going to make mistakes, and that's okay. The critical thing is being able to debug those mistakes and be able to see what the heck is going on. Okay, so we start by loading up our destination into RAX. Okay, load it up into RAX. We take our source and we load that into RBX. Cool, we got that loaded into RBX. Now we're going to pull out of memory from RBX and push that into RCX. Put that into RCX. So now we've got some amount of bytes put into RCX. And now we're going to compare. Is RCX 0? No, we just pulled out the first 8 bytes of hello world, but there is even more now. And we put that here, so this is not 0. We're currently got some of this data we need to transfer. So this jump equals, this is not going to happen. This is not equal to 0. And so what we're going to do now is we're going to take this RCX value and we're going to put it into memory at RAX. So suddenly this appears right here. So at memory right now at this location, we've currently got hello, comma, space W. And now we want to increment our source and our destination by 8. Why 8? Because we're transferring 8 bytes at a time. We could transfer 1 byte at a time instead if we want to. There's a question? Yeah.
Yeah, there's a question. How to get this makefile and the JDA layout?
Yes. So that is a good question. I'll share it after class. The answer is I have this fancy file thing here. I'll share it after class. This thing right here is making it display like that. So GDB is a very powerful tool. It can display in all sorts of ways. This little script right here makes it display like it currently is. But yeah, that's a good question. I'll share it after class in the Discord. Okay, so now we're adding 8 to RAX. We're adding 8 to RBX. And now we're going to jump back to our loop start. So we're going to do it all over again. We're going to pull out of memory at RBX. We're going to say, hey, is this 0? Well, it's not 0. As we can see right here, it's clearly not 0. So we're not going to jump if equal. We're going to push that into memory again. So we've moved this. And now we're just going to keep stepping. And we're adding 8. And we're walking through this loop again. And we're comparing again with 0. We can see it's still not 0. So we're running through this again. We can see now we've transferred 24 bytes of information. We'll just keep watching this go. Is it 0? It is still not 0. So we'll just keep going. And then, let's see, hopefully we're close to it being 0. We can see it's still not 0. I'm getting a little bit nervous that we've got an issue here, but I don't really know how many bytes I wrote. Oh, wait, we've got 0. Somehow we managed to get to 0. So we're looking good. Now we should watch ourselves exit out of here. So if we step, we're going to jump if equal done. RCX is currently 0. So when we did this comparison, it's equal. We're jumping to done. We're out of here. So let's make sure that we transferred what we expected to transfer. We did not. It is, well, we kind of did. It depends on what you expected to happen here. We transferred hello world, but there is even more now And this \001, this is an octal representation, not that it really matters, but this is the value 1. For a byte, it is number 1. So if we look at this instead, 64 bytes at this address right here, we're going to see somewhere in here, this byte right here is a 1. So the reason for that is, well, I guess it turns out there happened to be a 1 byte right after this. We don't control whatever the heck is after here. So if we wanted to be very safe, what we could do is, well, let's see here. We can make sure there's a whole bunch of null bytes here. If we do, I think it's .dq 0. I think that's going to create a quad word. Let's see that that is true. No. Well, we can definitely do db, right? No. Is it just... We'll put a whole bunch of null bytes at the end. Make it simple. Cool. And now I'm going to show another thing. Since we're using GDB, I don't want to step through this a million times. That was like quite the process of step. Let's just see what happens when we're done. The way we can do that is in GDB. Since we are in GDB, we can type break space done, because we have a label called done. We're just going to break when we're done. And we're going to type continue, and we're not going to watch all of that unfold. We're just going to see whether or not our change fixed it. It did not. There is still a 1 byte in here. Hold on, I think it might, if I do ASCII, let's see. Break done, continue. What the heck is here? Nope. Okay, well, what we're going to do is we're going to look at test and look for our world right here. We do see a whole bunch of null bytes after here, so we would expect this to work. Let's watch it happen again. What we're going to do now is we're going to step here, we're going to step here. Let's watch every single transfer come through. So what we can do if we want to break specifically every time we're doing a comparison is we can break at this address right here. So we type break star this address. Now we set up a breakpoint right there, and we can continue and specifically watch every comparison. Because I'm wondering where the heck is this 1 byte coming in? So this one does not have a 1 byte in there. Does not have a 1 byte in there. Okay, does this currently... Oh, you know what it is? There's one other thing we didn't think about. It looks like... Oh boy. It looks like this is exactly 8 byte aligned. So if I do length of this thing, it is exactly 40 bytes. This is a multiple of 8. So right now where this 1 byte is coming from, something was in memory before. And actually this will be easier to see if I slightly modify this so that we can see slightly more data. I'm going to go to 1 line further. If we make it so GDB sees this, okay, look at this. This is where that 1 byte is coming from. When we start up the program, there's something already in memory. It's that 1 byte. And then we filled in this memory right here. And when you're interpreting a string, what a string means, at least in the world of C, and also very commonly in assembly, is some sequence of ASCII values that ultimately terminate in a null byte. So we managed to fill all of this in, but we don't have a null byte at the very end. We have this 0, 1. So if we watch this unfold again and watch all of these, let's watch all of the transfers happen. So we'll break here and we'll continue. So that fills in, that fills in, that fills in, there, there. And then finally, We'll also break done, and we'll continue. And so we filled all of this in, but there's still this byte right here. So we forgot one final step. What we need to do, and this isn't exactly how memcopy works in C because we're doing this like 8-byte aligned instead of 1 byte aligned. What we need to do is we need to add our null byte also. So what we're going to do is we're going to, when we compare here, jump equals done. If we finish, what we need to do is we need to move into RAX just a bunch of zeros. 8 bytes worth of zeros. And if we want to say 8 bytes worth of zeros, we need to say keyword pointer. Okay. And now if we run this again and we break done and we continue. Wait, did we not move our, oh, well, we still have to execute this instruction here. Now we've zeroed it out. Now if we print this out, we have transferred this data across. Does anyone have any questions about this? I know there's a little bit of confusion in there. We did assembly writing, we did debugging. The two processes are very intertwined. You need to debug while you write your code because more likely than not, you're going to make some mistakes and you need to be able to recover from those mistakes. Does anyone have any questions about this? Any thoughts that come to mind? Yeah, there's a question.
Where did the 1 come from?
Yeah, that's a good question. So where the heck did this 1 come from? Let's go ahead and start it. If we look at memory, so is kind of a long-winded answer to this. This right here, so in the world of C, if we write our program, so let's code test.c. Oops. Code. We not, yeah, we have test.c. Oh, code server. In the world of C, this right here is a little bit of a lie. There's also int argc, car argv, car pointer argv, and if you really look at it, car envp. These things start up when your program launches. These things are coming from the kernel ultimately. Now, technically there's a C runtime and it's being passed to something else and it makes its way to main. And we don't have that machinery of libc's runtime. But these values of argc, argv, and envp, they come from the kernel. The kernel starts our program. And this value right here, I'm just going to tell you, is argv. So if we want to see maybe some more evidence of that, to see what else is passed here. So if we do, how to show this? We'll do 30gx at this address right here. So there's a 1 here, and then there's this thing, and then this thing, and then this thing. There's a whole bunch of stuff on the stack. So this is me showing what's in memory past this. There's way more stuff. And eventually we get out here. And eventually even further on, this right here, I'm going to tell you this is ASCII. It looks very ASCII-y. As you progress in this class, you work more with ASCII. You see ASCII as hexadecimal. Eventually you'll develop this intuitive sense of what the heck is ASCII. If we look at what the heck this right here is in memory, so this location here represented as a string, well, that doesn't look so good. Let's pick a different one. This is mbly/test that we just got here at 80. Let's go slightly higher. Let's go to this plus 8. No, not that plus 8, I guess. 68. Let's go to 70 instead. Hacker live assembly test. And if we print out a bunch of these things, these are all of our environment variables. All of our environment variables right now are living somewhere in memory. And the way that they got there is when the kernel started this program, the kernel put our entire environment into memory. And that's how you can start accessing stuff like argv1 and argv2 and envp3 or whatever. That's all here. And also, let's actually let's show this slightly differently. I'm going to edit the make file. If I do, what is the syntax for this? I want to add some argv-ness here. This is a test. I think if I do, is it args? Let's see. No. Man gdb arg. Oh, I guess when we run it, we can do that. Well, yeah, let's do that. Okay, so we're going to change this back to how it was before. We're going to start up GDB again. And what we're going to do is we're going to run, this is a test and another test. So what this is doing is it's setting argv1 to this is a test and argv2 to and another test. And if we go through here and print a whole bunch of stuff on the stack interpreted as C strings, well, we need more than that. Whole bunch of things. Let's just keep going. Where the heck are they? Because we have so many null bytes that, there we go. So this is my entire environment. And this right here is argv0, argv1, and argv2. So, and then way up at the start, I guess we'll just do run normally. Oh, no, start I. Hold on, let's just start this again as normal. So this right here, though, is argv. So then here's what we're going to do. We're going to show this thing, and we're going to show 3 of them. So this is argv, or this is argc. This is argv. So if I look at this thing, this is a pointer. So this is going to contain, what the heck is this? This is pointing at home hacker live assembly test, right? So this is argc, this is argv. I think I'm not sure where envp is. Not totally clear, but hopefully you get the idea. The program is initialized with a whole bunch of stuff from the kernel when we started. This is how argv and envp make their way in. Okay, it's kind of more technical than we needed to get for some stuff that's there, but that is how that works. Okay. Does anyone else have any questions about how we wrote this memcopy program or anything related to what we've done? Like something that just doesn't make sense. Cool. All right. So that is memcopy. Now, this version of memcopy, as I said before, is 8-byte aligned, which means it's not the real normal implementation of memcopy, because if we do something like this, let's show an edge case where this is going to break. If we do hello world exclamation points, and then this is another string, we should not be transferring this as another string. That just shouldn't happen. Because memcopy, we're moving one C string, or I guess I keep saying memcopy. I really mean to say strcopy throughout all of this. If we run this and we break on done and we continue and we step 1 past done because we made it so it puts null bytes at the end as well, and we look at this right here, we're going to see that we got hello world, this is another string transferred, when we meant to move just hello world. And one reason for that is we kind of intend to have a null byte here. So ASCII doesn't put a null byte at the end. If we do .string, it'll put a null byte at the end. And so this is going to kind of fix our issue, except not really. So if we do this and we break it done and we continue and we step 1 more, we're going to see when I print this location in memory, it just says hello world. We might think, wow, it succeeded. It only transferred hello world. Except if we print it as 2 strings, this is another string also got transferred. And the reason for that is because the null byte that says, hey, this is the end of our string is somewhere in here. And when we're comparing with 0 in our stir copy implementation, so I should probably rename this to stir copy since that's what I really meant, stir copy loop and stir copy loop. When we're comparing with 0, all 8 bytes need to be 0. So that's 8 byte aligned. When really the real definition is it should be 1 byte aligned. As soon as you hit a null byte, a single null byte, you're done transferring. We can fix this by doing a very simple thing. We can, instead of adding 8 every time, we're just going to add 1 every time. And instead of taking 8 bytes out of memory. So technically there's kind of this implicit, as we talked about before, keyword pointer. Really what we want to do is do a byte pointer. We want to only pull 1 byte out of memory. What we can do is instead of moving into RCX to do an 8 byte transfer, we can move into CL. So as a refresher from last week, we have RCX is 64 bits, ECX is 32 bits, CX is 16 bits, CL is 8 bits. So this is just 8 bits, 1 byte. So if we move there and then we compare CL with 0, and then we move CL into RAX, and then we only increment 1 and 1. Now, instead of moving 8 bytes at a time, we're moving 1 byte at a time. Now, you're going to notice that this is slower, right? Now we need to execute this loop 8 times as many times. So this is like less efficient. We're not fully utilizing our hardware. We're doing 1 byte copies at a time when we could be doing 8 bytes. Hopefully it's clear, and we're not going to do it. But you could imagine checking all 8 of these bytes and checking if any of them are null bytes, and in that special edge case, then doing single byte copies at a time, or something like that, so that you can still do 8 byte copies at a time, run less loops, do less instructions means faster program, generally-ish. And so you could write some optimized version of this, but we're not writing the optimized version of this. We're just writing something that works. And so if we go ahead and run this now, and we make, and we break done, and we continue, and we step past one more instruction because this is where we move that last little null byte, just in case. And it turns out it didn't really matter because it was already a null byte there. But to be safe, we should move our null byte. Now if we look at x/s this, we got hello world. We print 2 strings. It's hello world, and then we didn't transfer our second string. So we lost some performance here a little bit, but at least we're doing it correctly. You can decide if you like performance more or correct implementations more. For this case, for this class, for getting flags on this next module, you're going to prefer being correct over being fast. Okay, so that is now a correct version of this. This is stir copy. This is an algorithm for doing stir copy. We could instead write stir length. So stir length is going to be pretty similar with some minor changes. So let's, instead of this, let's say stir copy loop, stir copy done, stir length loop, stir length done. Let's write, just real quick, another algorithm. Instead of the copy algorithm, let's do the length algorithm. How long is this string? Well, it's going to look very similar. We're going to take 1 byte out of memory. We don't really care about this RAX anymore. We're not transferring to anywhere, but we'll keep using RBX. The very end, we're going to add RBX1. Oops. We're going to add this. We're going to jump to stir length loop. So we add 1 to RBX. We jump, and then what we need to do is we need to keep track. We also need to compare. If it's 0, we'll make this correct here too. In fact, you know what? Let's just get this out of here. We'll put it over here just in case we decide we want it back later. And we don't really care about where we're transferring to, so we'll also get that out of there. Cool, just in case we want that back. we're going to take this out of memory, put it into CL. We're going to compare CL with 0. If it is equal to 0, we're going to jump to stir length done. And we're missing one extra little thing here, which is let's make RAX start out at 0. So the base case is our string is 0 byte long in this case. And then we also then need to add RAX 1. So every time we go through this loop, we're adding 1. As soon as we detect a null byte, we jump out, right? It's kind of a straightforward algorithm. It doesn't really take that many instructions to implement stir length. Just keep checking every byte. Is it a null byte, not a null byte? As soon as you get a null byte, jump out of there. And then we are saving the result, in this case, into RAX. So let's go ahead and run that. So we will step through a few iterations of this. So we initialize RAX to 0. So currently the length is 0. We have what the heck we're trying to measure the length of here in RBX. We take 1 byte out of memory, so that's currently in RCX, so CL, which is part of RCX. We compare it with 0, currently not 0. So we're not jumping, so we're adding 1, going back to the start, keep doing this, and we're going to see that RAX just keeps incrementing. So I'm like doing that. Let's go ahead and break done. So I guess we don't have it done. Break stir copy done. What the heck did I call it? Stir length done, right? We're doing stir length now. Break stir length done. Continue to that. We're very happy that it didn't loop forever. That's a good sign. If we hit continue and it just sat here and didn't give us this little GDB prompt asking for our next command, we'd be thinking maybe I wrote a bug because it seems like this is running forever. But it did, in fact, terminate. We got the answer 0xd in here. So if we look at that and we confirm for ourselves using Python, how long is this string? Do we get this correct? So this is 13 represented as hex 0xd. So Python agrees with us that our implementation was correct. And we could try maybe a couple more things. We could try the empty string. This should return 0. So let's go ahead and make sure that returns 0. Break stir length done. Continue. Guess what? The result is 0. Let's put in, this is some longer string. And it ends now. We run that, break stir length done, continue. It says that's 2a. Let's see, is this 2a? Hex length. Double copy that. And it's 2a. So we just quickly wrote stir copy, we wrote stir length. Pretty straightforward, hopefully. If it's not straightforward, I'm going to ask again, does anyone have any questions about it? Because, of course, I say it's straightforward. I've been writing assembly for years. It might not be straightforward to some, right? This is the first time we're seeing this for most people. So if there is a question, feel free to ask. I'll just ask again if there's any. Yeah, we got a question. Yeah, so this is more to do with the assembler than it is to do with x86. So if we look at what the heck this produces when we obj dump this thing, so if we do obj dump -d mintel, or actually we can just make it and see what the heck it is right here. You're going to see that it automatically did move RBX 0x401020. So we didn't write that. We said offset hello. The assembler is smart, and it goes and figures out where the heck hello is, and it just swaps out offset hello with the address of hello. So this is like an assembler thing. We could instead, to be clear, have done this. Whoops. We take this value. We don't say this. We could just put this value in here and everything would just work. It's just this is kind of like a nice little version. So in case I do like this is, or I guess label 42 string test, right? If I start putting other things in memory, this hello is going to move around. It's no longer going to be at that address that it determined. So offset hello just very nicely figures out the location of it. It's kind of a convenience thing. Any more questions about what's going on here? Does everyone feel confident that they could, without watching this lecture again, implement stir copy and stir length? I'm pretty sure the last challenge of this entire, or maybe it's not the last, somewhere near the end of this module is implementing stir length. So it's going to be looking a lot like this. There was a question in the back. Yeah.
We're doing this between
Yeah, so if you want to, there is another module. So we're on the assembly crash course. We are going to be using parts of it in the reverse engineering module. So in fundamentals, we've got this debugging refresher. If you want to do it early, you can go ahead and do it early. These 8 levels here walk you through using GDB. It's your choice if you want to do that or not. These levels will be assigned to you later as part of an upcoming module called reverse engineering, where using GDB becomes even more critical. But it's kind of up to you if you want to get a head start on it to kind of get refreshed with GDB or not. Otherwise, I mean, everything I've done here, really all we're doing is we're breaking, we're continuing, and we're step instructioning. So like SI is to step an instruction, break somewhere, continue to a breakpoint. I've been using this x/ thing to print things out. So x/s prints it as a string, x/gx prints it as an 8-byte value, xbx prints it as a single byte value. We can do 20 of those single byte values in a row. And that's pretty much it. But yeah, if you want to, you can definitely do it early. Is there any more questions about writing assembly? Yeah, question. Yeah. Yeah, so the way I'm compiling it is I have this makefile, and really all that matters, you don't need a makefile. All we're doing is we're invoking the assembler against our source file to produce some object file. So as test.s is this thing. -o, test.o is this intermediate file that still needs to be linked. And then we run the linker against test.o and tell it to produce test. So it's 2 steps. We could do as test.s -o test.o ampersand ld test.o test. And that is how we do it. There's one more thing that you're going to need actually in these levels. So the way that these levels work is it expects to take in kind of the raw bytes of it. It's not taking an ELF in these levels. It's going to take the actual raw bytes of your program. And the way that we can do that, so we saw obj dump, test less. We saw that this allows us to kind of see the raw bytes, but probably you don't want to like copy these raw bytes by hand. Instead, what we can do, I think the challenge actually tells us how to do this. Let's confirm. Yeah, when you start up the challenge the very first time, it talks about this. So it says, hey, you're going to use the assembler. It shows one more thing. I guess it isn't even invoking the linker because you don't technically need to link it. So I guess, yeah, we don't need to link it. It shows this other command though. And what this other command is doing is it's pulling out the raw bytes. So I'm going to copy this and it's going to be slightly different. And you'll see it says, give me your assembly in bytes. It shows you how to do this. You're going to like cat this bin thing into the challenge and then the bytes end up. It's kind of a weird format, but the challenge tells you how to do it. And it should be pretty straightforward. What this is doing right here, if we take test and test.bin and we look at test.bin, It's a lot smaller than the elf file was before. You'll see it doesn't start with the string elf near the beginning. What this is doing is it's just taking that .text section, it's taking all the raw bytes in that text section and just dumping it to another file. And then what you end up doing is catting it and piping it into the challenge program so that all these bytes, all these like x60-ish number of bytes end up in the program. So that is how you actually interact with these challenges. I'll say there's one more thing that is very useful and probably should be mentioned. This entire time I've been using GDB to do things. And I've been setting up breakpoints myself. So for example, I've been doing break, stir length, done, and then continuing to that. If we don't want to set up a breakpoint ourselves, you can put int3 right here. It's an instruction. It does an interrupt, and it does a debug interrupt. Oops, let's go back to here. If I run make now, and I continue, so I didn't even set a breakpoint, I just continue, it stops on that int3 instruction for us. The way GDB works under the hood is it puts an int3 instruction in temporarily and then pulls it back out. So this is something you can do, and the challenges actually support it. So if you use an int3 instruction in these challenges, it's going to give you some debugging output of all of your registers' current values at that point when that interrupt hits. The challenge is kind of like designed to make things a little bit easier in that way. All right, if there's any more questions, message on Discord or I guess come up to me after class. Thank you all for attending, and good luck.